very easily create 10 or 20 gigabyte custom images. And then you start having to move these things around to deploy them. And then the people that run your network operations team hunt you down with a machete. They are very, very good, though, at working with the abstracting out technology stack. Just like the RPM, we don't really care. We launch the custom image, it's just running. I don't even know what operating system it's on. So it's really good as an abstraction layer. Good for devs, good for ops, this can vary. Certainly, these images can take a while to build. And so if this is the only way you've got of spinning up an instance of a server, that's going to really impact the productivity of your developers and testers. So you probably need another way of launching an instance of a service. The problem, though, is that actually a lot of virtualization technology is somewhat heavyweight and isn't very cost-effective at slicing these things up into very, very small parts. That's partly because the way most virtualization works is it uses a thing called the hypervisor. The hypervisor vises things hyperly and separates out virtual machines. Its job is mapping physical resources to virtual resources. Its job is isolating machines from other virtual machines from other virtual machines. The more virtual machines you have running on a physical machine, the more proportion of your resources are going to fuel that hypervisor. And therefore, fewer resources are actually going to fuel your virtual machines running your services. So it actually becomes very cost inefficient to have lots of small VMs. And also, we still have the issue that creating those custom images isn't as easy as it could be. This is sort of why people become interested in container technologies like Docker for this very purpose. Docker sort of gives you the ability to create these isolated execution environments, but to do so not only in a more lightweight way in terms of the developer tool chain, which is quite nice. It's nicer certainly than the creating most custom images out there, but it also gives you the ability to actually much more densely pack these isolated execution environments on physical hardware. That is because there is no hypervisor. The work is being done by a shared kernel to keep things isolated, and so actually you're spending more of your money to actually run a service than to maintain isolation between those services. So our cost of isolated hosts is drastically reduced, not just in terms of the work we do, but also in terms of computing resources. These things are mostly fairly easy to create. There are a couple of gotchas, but I'd say they definitely qualify as being fairly easy things to create. It's just a nice list of commands you need to run. They are very, very easy to deploy. As anyone who's installed large quantities of software from the public Docker Hub that are riddled with security backdoors, they are very easy to install. Just a little tip, if you do install stuff off the public Docker Hub, it's like taking a USB stick out of the gutter and sticking it into your production hardware and going, it'll be fine. It's very good at abstracting out the technology stack. We have the same capabilities here as our custom images. We launch it and run and it's good. Good for dev and good for ops. This is where things get a little bit more interesting. Developers love Docker. Developers love installing stuff from Docker Hub. They go, look how amazing I am. And then all the operations people go and say, okay, so how on earth do I run and how on earth do I manage this thing? And this is the problem, because the story around managing Docker in production hasn't been great historically, especially when we go beyond a single machine. The Docker engine that many of you have played around with on your laptop only really spans one machine. Getting your head around some of the networking stuff and orchestrating deployments across multiple allows us to model our environments in different ways. We would like something that makes handling lots of things easy, right? If we're going to get aggressive in microservices, we need to reduce the overhead of handling these things. And of course, something that handles Docker images. So what are we going to look at? We're going to look at 3 platforms. Firstly, we're going to look at Docker Swarm. About today. So let's start off with Docker Swarm. So Docker Swarm The really nice thing straight away about Docker Swarm is you would have got used to a command line for managing Docker images and deploying Docker containers on your laptop on a single machine. You've got commands like Docker log, Docker ps, all those commands. Those commands work at the Swarm Manager as well. The same command line, more or less about 70 to 80% of that command line works at the Swarm level as well as at the local machine level. Because what you don't want to have to do when you're handling lots of these things is say, I want this service here, and this service here, and this service here. Instead, what you want is an abstraction to say, look, I want this service deployed in a certain way, and I want you to manage where it goes. To give you an example of one of these sort of scheduling strategies, Swarm supports a bin pack strategy. Obviously though, this wouldn't necessarily be good if what we want is resiliency. What if we want, say, load balancing stuff going on? We haven't necessarily got a sense that our nodes are evenly spread out. Luckily, we have a spread scheduling policy. In a version controllable artifact. I would give you caution though. I would use Docker Compose to create a topology for a single service, not for my whole environment. If you have a Docker Compose file for your whole environment, you're kind of saying we're going to deploy the whole environment together. You're What you want when you're managing things at scale is the ability for these systems to be what we sort of call autonomic. That is self-healing. So when I say I want 15 of these nodes running, it means that if later on one of those nodes dies, I would like the platform to restart that node. Or if the actual physical machine they're on vanishes, I would expect my platform to start up another instance and redistribute the load according to my scheduling strategies. The story around Swarm wasn't great around that, which actually made it really wasn't very useful for large installs. It sort of does now do that, and it sort of does now restart failed containers, but this support is quite new, and I am very risk adverse when it comes to buying into a production deployment platform. One was by Rackspace, who were using Docker Swarm to build a platform as a service. That's great. The second was from my own publisher, O'Reilly, who were using it for their new online notebooks. And I thought, great. And I dug a bit deeper to find out that O'Reilly were actually using the Rackspace PaaS. So effectively, I had been given 2 case studies for the price of 1. Anyway, let's move on. Let's look at Mesos. In many ways, the most complex, but also behind the scenes. So again, a similar architecture. We have a Mesos master. A framework is not what I would ever call a framework, right? It's a very different thing. When I think about framework in Mesos speak is a scheduler. That is something that knows how to dispatch jobs for a given type of task. Is in running things like big data farms. It's in running things like Hadoop, Swarm, Spark. People who want to run tens of thousands of like big data processing nodes will often pick Mesos as a platform. In terms of what we're looking for a platform for microservices, it has a framework called Marathon, which is for running long-running jobs, and it supports in that and idea is also very powerful. There's, for example, to give you one example, there's a little framework called Arithmetic for Mesos that's for running short-lived containers. And you're thinking, well, why would I want to run a short-lived container? What's the point of that? How many people here have heard of Amazon Lambda? How amazing is Amazon Lambda? Right, it's great. Oh, look, it's serverless because I've got no servers. Well, you know, you're paying for them. You just don't know, you can't see how that works, right? Arithmetic is sort of half of Amazon Lambda. It's the part that actually allows you get an API, you call it, and it fires off a one-shot container. How hard is that to then wire up to something like Kong or an API gateway to effectively give you an in-house Lambda capability? And that's just one example of why this framework plugin model is so powerful. So just to summarize on Mesos, this is really good. If you're running different types of workload, you get to invest in sort of one cluster technology, one scheduling technology, and you can mix and match different things. This is a really good thing, I think. It's very, very powerful. It is very widely used. You can see lots of case studies of people using it, not just for sort of large data processing workloads, but also for microservice workloads. Orbitz did a very good case study at Velocity last year that's available online, where they talk through their experiences of moving onto using Docker and moving on to Marathon and Mesos for their microservice stack. But it is quite complex to get your head around. You do need to start understanding, oh, okay, so I've installed Mesos, but now I can't do anything. Now I've got to run a scheduler with executors. There are more moving parts going on. And some people dislike the fact that it relies on Zookeeper, but you know, I'm okay with that. So of course, we should now talk about the new kid on the block, which is Kubernetes. I say new kid on the block because it kind of is and it kind of isn't. Some people get confused and say, Google have open sourced their internal container technology and we all get to use it. That's not what they've done. Because they're not daft, that's a competitive advantage for them. What they've done is they've taken the abstractions that they use for using containers inside Google and have created an open source cleanroom implementation of those abstractions. This is partly Google's play to try and encourage people to be cloud agnostic and not just go all in with Amazon. So this is sort of very old in a sense that this is based on abstractions that Google have been using for many years, but the framework itself is also quite new in that it's only really been around for a year and a half, and we don't actually have that many case studies right now on this. Architecture sort of looks pretty similar, right? We have an API server that talks to things called kubelets, which is quite cute. I like the idea of a kubelet. So sweet. Again, I can run commands, I'll have an API, a CLI that I can run against my API server that dispatches jobs. And then I execute things. And then, of course, it's going to be nice and simple, and I just run containers. No, I run a thing called pods. And this is where Kubernetes starts to get a bit more confusing in a different way to Mesos. What is a pod? Well, a pod is sort of named after a pod of peas. So your unit of scheduling, the thing you deploy onto a node, is a collection, a tightly coupled collection of containers or volumes. So I can say these three things are in a pod, and therefore when they get deployed, they always get deployed together. Now, the kind of interesting thing is when we want independent deployability, pods are of little use to us, because we probably only want to deploy one thing by itself. You can still do things like affinity, saying I want this pod not deployed where this pod is, and things like that. So you still don't have to do that using this mechanism. This is also how you do things like associate things like metadata, volumes, configuration. You would put that inside the pod as well. But it's still a bit of an odd concept. The pods themselves will die and get recreated, and you think about a pod as a unit of scheduling. So when you say I want to run my invoicing service, I say deploy 5 pods of my invoicing service, and now off they go. So pods, I start looking at pods, and I think, oh, okay, that's okay. Maybe I could build my own abstraction on top to manage these things. But never fear, Kubernetes has that as well. Kubernetes has a concept of a service. So this is nice. So this is the definition of a service. This is obviously in JSON, because the people who created the documentation for Kubernetes hate human beings. I never understood this. Kubernetes does support YAML. Anyone who thinks this is more readable than YAML, well, we can take that outside. But what we see here are some interesting things. So I've got the name, my service, this is excellent, and I've got this thing called a selector. Now what's actually happening here is you're saying, my service is a logical concept, and it is constructed from a series of pods, and I pattern match onto those pods using this selector. So you say that my service is represented by pods with, say, this label on it. So in this case, I'm looking for the selector, my app. And so you've sort of got this loose connection. You've got pods and services, and it's kind of this odd, interesting selection thing going on. It's at the service level, though, that you do all the sort of port routing. This is where you expose how things are connected to each other, the protocols that you expose for it. So it's a mapping of metadata and ports to a set of ports, really. So the way this works under the hood is I have my machine, I have my cute little kubelet doing its work, I spin up pods, and the pods appear and they go, hello, I'm a pod. And then on that machine is a thing called a service proxy, and the service proxy goes, you look like a service. I'm now going to handle all the networking for you. So okay, great, okay, I'm getting there. My head's hurting still a little, but I've got pods, I've got services, so great. So I'm now, my service, whenever I build platforms, my service is king for me. That's the logical construct. I think about my service, I think about deploying a version of my service, I think about scaling my service. In Kubernetes, though, you don't scale a service, you scale the pods underneath, which means that you can easily get yourselves into a bit of a mess with your selection criteria. You scale up the pods that happen to not be the pods related to your service, and then the world gets very, very confusing. This abstraction doesn't work that well for me, and I'm not entirely sure why it's that useful. Some people who have been working for Kubernetes for the last 12 months say after 6 months it makes sense, which is it's not the best selling point. But anyway, it is a bit simpler to set up than Mesos. You don't have this idea of separate executors. It has a similar-ish number of nodes you need to run it. You're still talking a minimum number of sort of 9 nodes-ish for a production reliable setup. It's a little bit high-level abstraction than Mesos. So Mesos itself is quite low-level abstractions. People normally would build their own abstraction layer on top to make it a bit more like a platform. Kubernetes is a sort of higher level abstraction, which suits some people. The pod servicing is just downright confusing. It is quite new, but a lot of people have thrown their weight behind this. CoreOS have gone behind this. Red Hat realized that OpenShift v2 was a dead end, and OpenShift v3 is basically their implementation of Kubernetes. So you are now getting a lot of people who have got track records throwing their weight behind Kubernetes. Certainly, SoundCloud are looking at using this now. Okay, so let's cut to the chase. If Sam had to spend his money, where would he spend his money? Well, these are the 3 that I keep thinking about. Personally speaking, I would probably knock Swarm out straight away, purely because I'm very risk adverse with my production infrastructure. I would probably bake these two things off. If I was in an environment where I had a lot of mixed workloads and I had other problems to solve, like I had to scale out my data processing farms, I'd probably go with Mesos. But maybe if you're a straight microservice player, maybe Kubernetes. I would hold fire a bit on Kubernetes until we get a couple more case studies out. Summarizing very quickly, core principles, independent deployability, do that. One artifact for all environments, keep your environment config somewhere else. Use the same deployment process everywhere. Docker images as artifacts are excellent, and we've thought a little about the criteria for selecting platforms. Finally, all of this stuff is quite new, and there is a high degree of churn. Please do not be surprised if things go badly for you, right? These things can happen, especially if you pick the newer cutting-edge platforms. Be prepared for some mistakes. But I think with that, we're kind of at time. We have questions?
Yeah, there's some questions on the board. I'll read so you don't have to strain. What's your take on lock-in in the context of the platforms presented? Artifacts, containers make switching easier, but it's still a major buy-in and friction.
I think the buy-in is significantly less than some other platforms. Effectively, the lock-in level is the scripts you're using to drive these various different platforms. I think the other thing that's important to understand is that Mesos, and both Mesos and Kubernetes as the two examples I kind of call out as the best ones to look at. Yes, you're buying into that platform, but you also have lots of options about where you can run that platform. You can run that platform yourself. You can go and spin up an Azure or a Mesos or a Kubernetes cluster and run it there. So these platforms give you levels of portability of the underlying physical provider as well. I'm much more relaxed about the level of lock-in here than I might be with some of the other platforms I've looked at. The more work you're putting into building your own abstraction layer on top of a given platform, of course, I think the more trouble you've got. I think thinking of lock-in isn't necessarily helpful. Think about migration cost. So when you're going into a platform like this, think, well, at the moment, the migration cost of something else would be this amount of money. Are we okay with that? And have that in the back of your heads before you go too deep on one platform or another.
Okay, Sam. Jose asks, all these tools are great. What if you don't want to build it yourself?
Firstly, you don't have to build it yourself. You can get hosted Mesos, you can get hosted Kubernetes. Those are offerings out there already that you can get. Google does them, Azure does them. Amazon ECS is kind of new in this space. It's not quite there for me. It doesn't have the autonomic capabilities. So the way auto-scaling works is you can bring up the EC2 instances running your ECS clusters, but that's not quite the same as the capabilities that Mesos and Kubernetes gives you around sort of handling failure modes yet. I'm sure it will get there. I am more worried about lock-in of ECS than I am with Mesos and Kubernetes, because I can still lift it off to another Kubernetes or Mesos platform.
Next question. With Docker Swarm Master Mesos Master API server, is it possible to avoid single point of failure, like Swarm Master being down?
Yeah, all of these systems use sort of a quorum approach. So normally in production for Docker Swarm, you'd run 3 nodes, and they're backed as well by consensus systems like, so Docker Swarm can support Mesos, etcd, Zookeeper, or Console. Mesos masters, you'll normally run 3 of them. It's exactly the same for the Kubernetes API servers. All of these systems have that built in. Docker Swarm Stories got better in that area. There used to be some issues around that. That's got a lot significantly more reliable.
We have time for just a few more questions. Tony asks, the move towards microservices are usually due to dismantling a monolith. How do you make your microservice platform play nice with the monolith?
Good question. Do it really gradually. So I'm very serious with this. I think if you've got a monolith and you want to move to microservices, pull out one little microservice and ship it into production. Patterns like the Strangler pattern can help. Like if you have some sort of proxy layer that lets you intercept calls that are going to your old monolith system that you can redirect to your new microservices, this allows you to incrementally break apart your system while still keeping a facade to the outside world that looks seamless. I would never do a big bang rewrite. It's a terrible idea. Do it incrementally, do it gradually. Use some facade like that, and that can help a lot.
How about
Chapter 5 in the book. It's on sale.
Well done. Let's try Momoya's question. Can you see that one?
What's your view about Rocket? So for those who don't know, Rocket is CoreOS's sort of container format. They were worried, or at least their public view was that they were worried about some of the security decisions that were made with Docker, some of the issues with how users are managed and things like that. They felt that those concerns weren't being addressed, and so they decided to create their own underlying container format that was built from the ground up with more security in mind. Now, certainly the Kubernetes project has said that they will support Rocket as an underlying format. I think Mesos Marathon does support Rocket execution, although I could be wrong about that. I'd also say that a lot of the concerns that the Rocket team raised, the CoreOS team raised, have been addressed by some of the changes that are happening around Docker and Docker security. So personally speaking, I think that almost the value of Rocket was in terms of making people aware of some of the challenges around security.
That's all the time we have. Thank you, Sam.
Thank you.